everyone. My name is Akanksha Pathade and from ENTC department. Today I'm presenting my internship project titled Real-Time EV Dashboard and ADAS Warning System. The aim of this project is to improve vehicle safety by continuously monitoring vehicles, parameters and detecting nearby obstacles. The project uses an STM32 microcontroller, ultrasonic sensors, and Python dashboard to simulate the behavior of an electric vehicle with ADAS feature. Introduction. Before discussing this project, let us understand why it is important. Electric vehicles, commonly called EVs, are becoming increasingly popular because they reduces pollution and help save fossil fuels. As EV adoption increases, safety becomes very important. Drivers need real time information about vehicle status, battery condition, and surrounding obstacles. This is where ADAS comes into the picture. ADAS. ADAS stands for Advanced Driver Assistance System. ADAS helps driver by detecting obstacles, warning about position, collision, and improve driving safety. Examples of ADAS features include collision warning, parking assistant, blind spot detection, and lane departure warning. In this project, I have developed a simulator EV monitoring and ADAS warning system using an STM32 microcontroller. The system continuously monitors vehicle condition and provides alert whenever a dangerous situation is detected. Objective. The objective of this project are as follows. The first objective is to design a real-time EV monitoring system. The second objective is to a real design nearby obstacle using ultrasonic sensor. The third objective is to measure vehicle speed and battery status. The fourth objective is to warn the driver before a collision occurs. Another objective is to display all vehicle information on a live dashboard. Finally, the project aims to improve vehicle safety using embedded system technology. This objective combines sensing, processing, communication, and visualization into a single system. Now, I will explain the component used in this project. Hardware components are the main controller is the STM32F103C8T6 blueprint. This is a 32-bit ARM Cortex M3 microcontroller. It processes sensor data and makes decisions and control outputs. The project uses three HC-SR04 ultrasonic sensors. The sensor measures the distance of the obstacle from the vehicle. One sensor is placed at the front, one at the left side, and one at the right side. Potentiometers are used to simulate accelerator position, brake position, and battery state of charge and motor temperature. LEDs are used as a visual indicator. Different LEDs represent normal condition, warning condition, blind spot detection, and fault condition. A buzzer is used to provide an audible alert whenever a danger situation occurs. The ST-Link V2 programmer is used for programming and debugging the STM32 microcontroller. Software components. STM32Cube MX is used for a peripheral configuration. STM32 IDE is used for writing and compiling the embedded C program. PiximLab is used for hardware simulation. Python is used to create the dashboard. PySerial is used for UART communication between STM32 and Python. Matplotlib is used for displaying data graphically. Working of a system. Now, let me explain the working of the system step by step. First, the STM32 reads value from potentiometer. This value represents accelerator position, brake input, battery level, and motor temperature. Next, the ultrasonic sensors measure the distance of obstacle around the vehicle. The microcontroller processes all these inputs and calculate vehicle speed and battery status. Then the system checks whether any obstacle is too close. If the distance becomes smaller than a predefined threshold, a collision risk is detected. The system then generates warning alert. Visual alert are provided through LEDs and audible alert are generated using the buzzer. After processing all information, STM32 sends data to the computer through UART communication. Finally, the Python dashboard receives and displays the information in real time. This complete cycle repeat continuously, provide live monitoring and safety alert. Read, accelerate, brake, battery and temperature values. Read obstacle distance using ultrasonic sensors. Calculate speed and battery status. Detect collision or a blind spot conditions. Generate warning using L. Sends live data through UART. Display data on the Python dashboard. ADAS and buzzer. PiximLab simulation. It simulates the STM32 blueprint. Potentiometers stimulate accelerator, brake, battery, SOLC, and motor temperature. HC-SR04 sensors detect front, left, and right obstacles. LEDs display warning status. Buzzer gives audible alert. Virtual terminal displays like UART. Since, sorry, since physical hardware was not used, the project was implemented in PiximLab. PiximLab is a simulation environment for embedded system. In the simulation, potentiometers simulate accelerator position, brake position, battery state of charge, and motor temperature. Three ultrasonic sensors simulate obstacle detection. The LED indicate different warning conditions. The buzzer generates warning sound. The virtual terminal display UART communication data sent by the STM32. Using simulation allows us to test the complete system without requiring actual vehicle hardware. It also reduces development cost and simplifying debugging. ADAS features. This project implements several ADAS features. Examples are collision warning, blind spot detection, parking assistant, battery monitoring, motor temperature monitoring, drive modes, fault detection, real-time dashboard. In collision warning, when an obstacle is detected very close to the vehicle, the system generates a warning. This helps the driver react before a collision occurs. In blind spot detection, vehicles are often have areas that are difficult for drivers to see. Beside, ultrasonic sensors helps detect object in this blind spot. In parking assistant, during parking, the ultrasonic sensors measures distance and assist driver. In battery monitoring, the system continuously track battery state of charge. This helps monitor vehicle energy availability. In motor temperature monitoring, motor temperature is monitored to prevent overheating. In drive mode, different drive modes such as eco, normal, and sport can be simulated. Each mode affects vehicle different behavior. Fault detection. The system can identify abnormal opening conditions and provide alert. Real-time dashboard. All information is displayed on the dashboard for easy monitoring. This project has many applications. For example, electric vehicles, smart cars, driver assistance system, parking assistant, automotive research, embedded system education. Electric vehicle can be used for safety monitoring. Smart car with driver assistant feature can be used. It can be used in a parking assistant system. It is useful for automotive research and development. Educational institute can use this project to teach embedded system, sensors, and automotive electronics. The same concept can be expanded into autonomous vehicle system. Advantages. There are several advantages of the project. It improves road safety by providing early warning. It detects obstacle in a real time. The system is low cost because it uses affordable sensors and microcontrollers. The project can be upgraded and implemented on actual vehicle in the future. It also demonstrates how embedded system can improve transportation safety. Conclusion of this project. To conclude, this project successfully demonstrates a real-time EV monitoring and ADAS warning system. The STM32 microcontroller collects and processes sensor data. Ultrasonic sensors detect nearby obstacles. The system generates warning alerts using LEDs and buzzers. A Python dashboard displays vehicle information in real time. The project demonstrates how embedded systems can improve the electric vehicle safety and can be expanded into real-time automotive application in the future. Simulation of my EV ADAS project. The screen shows the Pixim Lab simulation of my project. Pixim Lab is an embedded system simulator that allows us to test and complete hardware design without using actual hardware. In this project, I have used STM32 Blue Pill microcontroller as a main controller. This is the STM32F103C8T6 Blue Pill microcontroller. It is the brain of the system. It reads all the sensor input, processes the data, detects obstacles, and controls the output, like LEDs and buzzers. It also sends vehicle data to the dashboard through UART communication. On the left side, this potentiometer simulates vehicle inputs. The first one represents accelerator pedal. This one. The second one represents the brake pedal. And the third one represents SOC, state of charge. And the fourth one represents motor temperature. By changing this value, I can simulate different driving conditions. Now, these are three HC-SR04 ultrasonic sensors. The front sensor detects obstacle in the front of the vehicle, while the left and the right is used for blind spot detection. The STM32 measures the distance from the sensor and checks whether the vehicle is in safe condition or if warning should be generated. This LED indicates different system conditions. The green LED shows that system is power on. The yellow LED indicates the warning, the blue LED indicates blind spot detection, and the red LED indicates fraud or a critical condition. The buzzer provides an audible warning whenever an obstacle is detected or a critical condition occurs. On the right side is the UART virtual terminal. It is the real-time vehicle information speed such as speed, battery, percent, torque, power, range, obstacle distance, and the current vehicle state. This is used to verify that the embedded software is working correctly. And the complete working is very simple. The STM32 reads all the sensor input, process the data, detect obstacle, and decide whether the vehicle is in normal warning or a fault condition. Based on this, it controls the LED and buzzer and sends the live data to the dashboard. This demonstrates how an advanced driver assistance system can improve the safety of an electric vehicle. Thank you for your attention. I hope this presentation provides a clear understanding of the real-time EV dashboard and ADAS warning system.